you will find them missing. You will find termination register in some board missing. How is that? And what is the use of termination registers? What exactly is the purpose of termination register? Now listen to my words very carefully, what I am speaking till now, right now. See, in a notebook motherboard, we'll take the case of a schematic diagram. Let's take DB2000 case, and the RAM slot you see in this schematic diagram. In this schematic diagram, you can see in notebook motherboard, this is the data communication between GMCH and RAM is taking at very high frequency. It is taking at a very high frequency. So it is taking as a very high frequency, so we cannot use the concept of lumped circuit. What is lumped circuit? We mean by lumped circuit is that voltages is fixed at each of the point. Well, there is a direct connection between GMCH to the RAM, but we cannot consider voltages to be same between here to here because the data communication is taking place at a very high frequency. So it cannot be considered as a case of lumped circuit. Lumped circuit, lumped circuit is considered where you can consider the voltages between here to here as same, but we cannot consider here the voltages to be same when the data communication is taking place at a very high frequency. There is differences in voltage, right? There is differences in voltage, so we have to consider this as transmission lines, right? Transmission line. As a transmission line, what is transmission line? Transmission line is a very is a situation. You see how electricity comes to our house from a powerhouse. It comes to transmission line. The current flows miles, kilometers before reaching our house. So we can consider this small distance between GMCH and RAM to be a transmission line, not to be a lumped circuit, not to be a small circuit, because the data communication takes place at a very high frequency. So we have to consider as a transmission line. And in transmission line, in order to offset the resistance, we use the termination register. In order to offset the resistance and capacitance in between, we use termination registers, right? We use termination registers. So you can see what is it, because there is a impedance mismatch. Well, I won't go into much detail, but we can also derive this as mathematically, and we had done this derivation mathematically in the class of transmission power while I studied electrical engineering. So that's why I had correlated the concept of termination registers. Why termination registers is required? Termination register is required because the distance between the DDR RAM slot and the GMCH can be considered as a transmission line, because the data transmission takes place at a very high frequency and we cannot consider the voltages to be same. So in order to offset these differences, we have to use a termination registers over here. So just understand the very basic phenomena that we had to use a termination register. But in case of DDR1 RAM, we had external termination registers, while DDR2 and DDR3 RAMs have implemented termination register on die, right? On die. There is on die termination is the technology where the termination register for impedance matching in transmission line is located inside semiconductor chip instead of on printed circuit, right? Instead of on printed circuit. So the termination register are integrated on the RAM only. in DDR2 and DDR3, and that is why we call it as a on die termination, right? So regarding DRAM concept, we have studied three concepts right now. What is memory refresh? Memory refresh is required in order to preserve data on the memory, right? Memory refresh is required in order to preserve data on memory. Second is on die termination. In case of DDR1, termination registers are present on motherboard, whereas in case of DDR2 and DDR3, the termination registers are present on RAM only, right? And we have studied why termination register is used and required. So we go to the next slide, and if you miss anything, just rewind this video, because right, just rewind this video and you get what I'm trying to speak. And let's go to the next slide, and this is very important. What are the supply voltages for DRAM? Many people get confused. What are the voltages that is required for a RAM to work? And I will tell you, there is just a requirement of 3 voltages in order to run a RAM. In order to run a RAM, you require 3 voltages, and these 3 voltages are the most important. So always try to find these 3 voltages on any schematic diagram or motherboard while you are trying to check for a RAM. A RAM will only work when it gets these 3 voltages. These 3 voltages. What are the 3 voltages? VDDQ, termination voltage, and reference voltage. VDDQ, termination voltage, and reference voltage. What is VDDQ? VDDQ is the voltage used by signals on memory bus. That is, VDDQ is the voltage used by signals on this memory bus. This is memory bus, right? This is memory bus, and this voltage is also known as SSTL, stub series termination logic voltages, and VDDQ is commonly known as DIMM voltages or DRAM bus voltages. And for DDR1 this is 2.5 volt, for DDR2 this is 1.8 volt, for DDR3 this is 1.5 volt, and for DDR4 this is 1.2 volt. So as the technology upgrades, we move to a lesser voltages. That is the trend that we are following. Less voltage means less power consumption. Miniaturization, we are moving towards miniaturization, and miniaturization works on lesser voltage, and that's why you can see your smartphones or mobile phones, they work at lesser voltages, and they have a greater battery backup than a notebook motherboard, right? Because they work on a lesser voltages. So the first RAM, the first dynamic RAM, DDR1, it operates 2.5 volt. The VDDQ was 2.5. Always try to use the technical terms that have been defined. Technical term is VDDQ, and you can find it in a schematic diagram. Whereas if you search DIMM volt in a schematic diagram, you won't find. So always try to remember and develop a habit of using the technical terms that are generally defined. Right? VDD, and then we have termination voltage and reference voltage. So now you see VDDQ. Now we go to the termination voltage. The termination voltage is the voltage that is used to feed the termination logic inside the memory chip, right? Inside the memory chip. That is, the termination voltage is the voltage that is used to feed the termination logic inside the RAM, and we'll see all of these voltages, right? We'll see all of these voltages. And the third is reference voltage. What is reference voltages? The memory reference voltage configures both the memory controller and the memory module with a voltage level that separates what is to be considered as 0 or 1, right? So this voltage, reference voltages, basically configures memory controller and the memory module with the voltage that separate what is 1 and 0. As I said, the data is saved in the RAM in form of 1 and 0. But obviously this data has to be in form of voltages. So memory reference voltages define what is considered to be 1 and what is considered to be 0. That is, any voltage lesser than the reference voltage is considered to be 0, higher than reference voltage it will be considered to be as 1. So now we go into schematic and locate these three voltages, right? We'll locate these three voltages. So let's, okay, so these are the three voltages that we had studied. The one is VDDQ, another is termination voltages, and the reference voltages. So we had already understood what these three voltages mean. Now we go to the next slide, and the next slide is yes. DDR1 uses DDR1 uses 2.5 volt as the dim voltages. 1.8 volt is used by DDR2, and DDR3 uses 1.5 volt. So we go to the slide and we go to the schematic diagram, and we'll see these three voltages. So yes, this is a DV2000 schematic diagram, and we see 1.8 volt. This is the VDDQ or dim voltages, right? Or dim voltages. So you can see 1.8 volt. This is a VDDQ, and we go down and we'll see the V reference. V reference is, what is V reference? DDR underscore VREF underscore S3. We go down, we search how much is this, and we'll see over here. Yes, and this is DDR VREF underscore S3 is basically 1.8 volt, right? This is 1.8 volt. 1.8 volt. We can also go and find over here. Wait. DDR. This is DDR VR underscore VREF underscore S3, and this voltage is generated by this IC TPS 51100DGQR. So what are the three important voltages required for a RAM to operate? VDDQ, then we have reference volt, and then you have termination voltages. So we had already seen 1.8 volt underscore S3 is required. You see over here, page number 14. This 1.8 volt underscore S3 is the must one. Then second one, V reference. And what is V reference? V reference here is connected to DDR underscore VREF underscore S3. We search it, and this is generated from this IC, and this value would be 1.8 volt. VDDQ is coming over here as V reference, VTT reference, and this value is 1.8 volt. So if this IC is faulty, then this reference volt won't generate, and when your reference volt won't generate, your RAM won't operate, so display won't come, right? And we'll see the another volt that is termination volt, right? And termination volt is also generated from there. You see, termination voltages. Termination voltage is VTT 0D9V underscore PWR. So this IC is generating the RAM reference volt and termination voltage 0.9 volt and V reference, right? V reference. As you can see in the next slide, for DDR2, since this schematic diagram is using DDR2 RAM, for DDR2 we have VDDQ as 1.8 volt and termination voltage as 0.9 volt. 0.9 volt, right? And the reference volt is 1.8 volt. Similarly, the reference volt for DDR3 is 1.5 volt. And this is in the schematic diagram we are seeing the reference volt and the termination volt is generated from the same IC, right? So three voltages are required. We go and find in our next schematic, and our next schematic is Lenovo Y570. Here also we can find our three voltages. One is VDDQ 1.5 volt underscore sus. Here in our slide you can see, for DDR3 we require 1.5 volt as VDDQ or dim voltages. You see, this VDDQ is also called as dim volt. So for DDR3 we require 1.5 volt. So in a schematic you can see this VDDQ is powered by 1.5 volt. Now what is our next volt? Next volt is termination voltages, and you see VTT, this is connected to 0.75, and here in our slide you can see the termination voltage for DDR3 is 0.75. Again in our schematic we have to look the third voltage, that is reference volt, and here it is connected to VREF. You see, VREF DQ, VREF CA. Now we go to find what is VREF. This is SMDDR underscore VREF underscore DQ1 underscore M1, and this is connected to SMDDR VREF. Now SMDDR VREF, what is this? We see and this is SMDDR underscore VREF. Now this is coming as same 1.5 volt underscore sus, right? 1.5 volt underscore sus. So we can see this is same 1.5 volt underscore sus. So we can see what are the three important voltages. The three important voltages are VDDQ, termination volt and reference volt, right? VDDQ is, what are the three important voltages? VDDQ, termination volt and reference volt. So VDDQ is also called dim voltages, right? And we have to check for all these three voltages, in the next slide. Now we'll also note about a very important difference between DDR3 memory and a DDR2 memory, DDR3 memory and a DDR2 memory. So let's go to the data sheet and we find the differences between DDR3 and DDR2. Now this is the initialization sequence for a DDR3 memory. This is a initialization sequence for a DDR3 memory, and this is the data sheet I have got from my internet, and there are basically sequences for a DDR memory. There is a sequence. So we'll go through this data sheet and understand the basic difference between a DDR2 and a DDR3, right? Okay, so now let's see one difference between the DDR2 and DDR3 RAM. Yes, there is a little bit of difference between DDR2 and DDR3 RAM, and I have opened this data sheet, basically power up initialization. See, every RAM has a different power up sequence, right? And we're not going to go into details of power up sequence for a RAM. Rather, we will just focus. See here in this data sheet, you can see there are around 24 steps before a RAM is powered on. And what are the important sequences? One is VDDQ, VTT and VREF. That we have already talked that every RAM requires three supply voltages. One is VDDQ, reference volt and VTT volt in order to operate. So these three voltages must come, and there is a pin called reset. While this reset pin is only available in DDR3 and is not available in DDR1 and 2, and we can see in our schematic diagram. Yes, in our schematic diagram you can see here there's one more signal coming, DDR3 underscore DRAM reset, and this signal is must from from, you can see here, it will come from memory controller. And as we know, in a PCH kind of board, the memory controller has moved on to CPU. So this signal will come from CPU, and then this RAM will initialize. That is, the RAM initialization process will take after CPU powers on, right? After CPU powers on, when CPU memory controller gives this signal, that is DDR3 underscore DRAM reset, and you can see from where it is coming. DRAM RST, right? And this will come from, you can see, this is CPU underscore DRAM reset, is same as DDR3 underscore DRAM reset, and there must be 1.5 volt. This is 1.5 volt connected, and you can see DRAM RST has, and this is coming from, you see, DDR3 section of CPU. So this is one major difference between a DDR3 and DDR2. There is no such RAM reset signal in DDR2 or DDR1 board, whereas you have a RAM reset signal in DDR3 boards. So you must check this reset signal in DDR RAM slots, okay? This must come. So what are our most important supply voltages? 3 voltages and this reset signal, and you can see over here there is a CKE. So we'll go into our PowerPoint presentation. You can see we have noted all the important specific signal: CKE, RAS, cache, write, enable. So while testing RAM, what should we be concerned about? First, supply voltages. 3 kind of supply voltages. We must see RAM reset signal in case of DDR3, and we can also look for these kind of signals, right? And you can see the RAM reset signal is coming out from the CPU memory controller, right? CPU memory controller. So there is a specific power sequence, and this SDA and SCL will also come at the SPD chip, and we will talk about when this serial data and serial clock signal will come, right? When this serial data and serial clock signal will come. We go to the next slide, and here is a presentation on basically RAM slot and the various voltages. You can get this printed out and you can measure, whereas you should be only concerned about 3 supply voltages. Those are very specific, very important. 2.5 volt for DDR1, 1.35 termination voltages, 1.8 volt is the DRAM voltages, 0.9 termination voltages, 1.5 is for DDR3, 0.75 is termination voltage, and we have to check another reference voltages also. And you have to check a very important signal called reset signal, RAM reset signal from CPU to DDR3 RAM, and these signals also. Now we have again some very important concepts about RAM, so we'll use these concepts to analyze the power sequence. And we go to the next slide, and this is a very general block diagram of memory controller. And basically I won't go into much details about memory controller, but for completing this topic I have added this slide. And basically memory controller is divided into 2 parts. One is front end and another is back end. And the front end is basically buffers, requests and responses, whereas the back end provides a interface with the target memory. Why I'm talking about is because you have seen same motherboard, same kind of motherboard can have DDR2 RAM or DDR3 RAM slot. You see, you must have observed CQ40 board, CQ40. This board comes into 2 kinds, one having DDR2 RAM, another having DDR3 RAM. So how does our GMCH IC know whether DDR3 RAM is there or DDR2 RAM is there? With the same GMCH, because you see the GMCH is divided into two parts. One is the front end, another is back end. Front end is same. Front end means CKE, CAS, RAS, write enable for generating all this kind of signal, and back end is for the specific kind of memory. And also the motherboard knows which kind of memory is installed by the SPD chip present on the RAM. By the SPD chip present on the RAM. That is very important. BIOS, SPD BIOS chip that is present on the RAM. And we will also discuss when this SPD BIOS chip will generate the serial clock and serial data, right? When this will generate the serial clock and the serial data. All are in sequence, complete sequence. No confusion between the sequence. The RAM SPD data and clock, you see, the RAM SD and SCL data will be generated after CPU is powered on, after reset signal is generated, right? After reset signal is generated. That is, this SD and SCL signal is very important. Is very important when you are debugging the no display scenario. So now we'll go to the details about clock generators, because before going into the schematic diagram, I'll discuss about clock generators, and then we'll finish up with the basic background that we have been preparing to understand the power sequences. So in this slide, I'm going to discuss about the clock generator. Okay, so before I start with analysis of power sequence, I'll just finish a little things about clock generator, because this is most important device that is present onto your notebook motherboard. And as we have studied in the very first class, that every electronic devices requires three things: supply, reset, and clock. And what is clock? Clock is basically related to timing, because you know, any digital circuit, they work in a predefined time. Like if any operation has been done, suppose we want to add two things in computer, like suppose we want to add two things in a computer, then a computer will take a fixed amount of time to finish that operation, right? Finish that operation. So how is that time counted? It is counted in format of clock, right? You have observed many times into your window operating system that sometime the window operating system gets hanged and it cannot perform the required task in that same time, because you know, every digital circuits are man-made. Digital circuits are man-made, and anything that is man-made has to be done in a fixed time. Time is fixed. When a human being produce or manufactures any device, we are going to do it in a time-bound format. And you can relate my statement with any kind of machine built by man. Any kind of machine built by man. We are all concerned about time, because these devices are made by human, right? So since it is made by man, time is a very important factor. And in a notebook or in a digital circuits, how time is counted? Time is counted in a form of clock. And how clock is generated? Clock is generated by a device called clock generator, right? It is a device called clock generator, and and you can see oscillator, clock chip, signal generator. These can generate clocks. Now what we will do is we will go into our schematic diagram and see how does a clock generator observes. I will discuss this clock generator once again while analyzing the power sequence, but right now we are going to the crux of this clock generator. And what is the crux of this clock generator is, I already say that any digital circuit requires three things: supply, reset, and clock. And over here you can see this is supply. Two kind of supply: 3.3 volt, 1.25 volt. One for the CPU core and another for the I/O. So 3.3 volt, 1.25 volt, and this is crystal. And it will require two more signals, that is stop underscore CPU, CPU stop, and CK power good. This CK power good would be generated by PCH over here, and how it will when it will be generated CK power good, when the PCH or ICH will get clock enable signal from VRM. That is, this clock generator will turn on after CPU gets power, right? How? You can see CK power good, CK power good, CK power good. You see CK power good is generated from here, CK power good, and you see clock enable signal is coming over here, then CK power good is coming. So we will see from where clock enable is coming, CLK underscore EN, and you can see this clock enable is coming from the VRM IC, right? From the VRM IC, that is the CPU core regulator. So when my CPU core regulator starts on and it starts correctly, then it will generate clock enable signal. That clock enable signal will help to generate CK power good, and when it gets CK power good, then my clock generator will turn on. Two signals, CK power good and stop underscore CPU, that is CPU stop. It gets two signal, supply and the clock, then this clock generator will turn on and it will generate the required clock which is needed by the devices present onto the notebook motherboard. And what are those devices? CPU, MCH, you see LAN, mini Wi-Fi, SATA, all of them requires clock to work correctly, and this is generated by clock generator. Now I will go to, so what are the important points when we are checking a clock generator? First, supply, crystal, stop underscore CPU, CK underscore power good, and we can check over here this output pin through CRO. It will give a sine wave, having frequency 48 megahertz. So if this sine wave of 48 megahertz is not coming, that is your clock generator is not working correctly, and in that case we have to see the inputs. And what are those inputs? Supply, clock, and CK power good and CPU stop. So once we check these three things, then my output should come over here. If it's not coming, then your clock generator is faulty, right? Your clock generator is faulty. Now we'll see our another schematic that we have been referring, and we'll go to see this R12. Actually, we are checking Lenovo Y570, which is having HM65 chipset. And while I discuss the power sequence, I will tell you that HM65 chipset won't require any external clock generator, because HM65 Intel Series 6 chipset have embedded clock generator, So we can, okay, so we have finished up with the basics, and now we're going to start the study the power sequences. So let's start off with ICH9. And I will tell you that Intel has data sheet for each of its chipset or IC that it develops. So we'll develop a mechanism by which we can understand those data sheets and we can find the valuable things for our purpose, because our purpose is to repair, right? Is to repair. We don't have our purpose is not design. So we'll look into the data sheet. See, the Intel chipset data sheet is having more than 500 pages. So you don't require to go through all those 500 pages, right? What we require is the basic conclusion, right? Basic conclusion of those data sheets. So my aim of the class is to understand each of the data sheet, and also to understand, suppose Intel launches new chipset, how will you go through those data sheets? So let's start with ICH9, and this is Intel controller hub 9 data sheet. You can easily get it through internet, and I would also send you this data sheet. You just have to browse into the Google write ICH Intel ICH 9 data sheet, and you will find this data sheet very commonly available. Now you see, this is page number 1, and page number 1 you can see what are the various kind of chips which are Intel ICH 9 family, and you can see over here 82801 IB, 82801 IBM, IEM, these are all IBM, these are all ICH 9. Okay, ICH 9. So you can also see the ICs which are the part of this family. So, and here are the details, here are the details that are covered in this data sheet. So we'll go straight away to the first page, 40 number, and here is ICH 9 features. So we'll just quickly go through those features. This is direct media interface. We had already discussed what is direct media interface. It is connection between the north bridge and the south bridge, and this is PCI Express. So this chipset, this ICH 9 south bridge chipset, you can see over here. We'll go to the page number 1, and this is having only ICH 8. This ICH supports this features, direct media interface, PCI Express, PCI bus, then host controller, then SATA support, then audio, and USB 2.0, and various power management logic is supported by this ICH 9, right? Various power logic. So this chipset, you see, this is at the center. USB, camera, TPM, audio, mini card, Wi-Fi, all is supported through this chipset. Card reader, everything is supported through this ICH. So here are the features which are mentioned in the data sheet on page number 40. We go to the next page, and in the next page we can see SM bus controller. We'll discuss about this also. And real-time clock, you see real-time clock is there. We have already tested how to test this RTC section. Now very important description is 1.05 volt operation with 1.5 and 3.3 volt IO. Please mark this statement, mark it, because we are going to use this line afterwards. So mark it, this is very important. And 1.05 volt core voltage, this is the core voltage for ICH, not processor. Do not get confused. You see over here, this Intel ICH chipset is having lot of transistors, MOSFETs inside it. So 1.05 volt is the core supply of this chipset. Core supply, you see any chipset will have core and IO, core and input output. There is a separate voltage for core section, there is separate voltage for the input output section. So 1.05 volt here mentioned is the supply for core, right? Core. And you can see over here, this ICH also has RTC section. The RTC section of ICH turns on initially. The RTC section of ICH 9 turns on initially. Core section do not turn on, right? Core section do not turn on, and RTC section is powered by 3.3 volt. 3.3 volt, and we are going to discuss about this in this class. Okay, so mark these two lines, 1.05 core volt, and you can also see 5 integrated voltage regulators. Yes, this is a very important point which people always overlook. And what is that? This chipset ICH has integrated voltage regulator, 5 integrated voltage regulator, right? What are the use of those 5 voltage regulator? 5 integrated voltage regulator to generate the LDO voltages, for working of parts internal to ICH, parts internal to ICH. You can consider this ICH to be a home having various rooms, and those rooms are not having electricity simultaneously, right? The RTC section room is the first room. It is powered by 3.3 volt, right? And the core is at the center, which is powered at last, and the core section is powered by 1.05 volt. This is mentioned in the data sheet, and we are going to check it in schematic also. So this is the way to look the data sheet. This is the process that we study any data sheet of Intel. What we have checked, these are the various features, and for understanding the power sequence, you have to check these 3 points: 1.05 volt operation, 1.05 core voltage, 5 integrated voltage regulators, right? 5 integrated voltage regulators. Now what we will do is we'll go through the block diagram. So let's go. First, what I have checked in this data sheet, first features, ICH 9 feature. So if you study any other data sheet, suppose you are going to study ICH 8, ICH 6, ICH 5, what you have to first check? This feature page. So you can search like this, ICH 8 features in ICH 8 data sheet, right? I'm telling you the strategy, the step by which we can study the details about any chipset, right? Now we have seen the features. Now what we are going to do is we go to see the block diagram, right? The block diagram will make things clear. So let's go to the block diagram, and this is, you see the block diagram for mobile. You will see the block diagram for desktop. Here we are concerned with the block diagram for the notebook, mobile notebook, right? Now you can see in this block diagram, the entire ICH is divided into certain blocks. What are those blocks? The blocks are PCI interface, processor interface, SPI interface, interrupt interface, USB, RTC, clock, miscellaneous signals, general purpose input output, platform LAN connect, and you can see GBE control, controller link, serial ATA interface, power management signals, high definition audio, direct media interface, firmware have, LPC have, SM bus, and system management. These are the various parts inside your ICH 9, whereas in a schematic, if you go in a schematic, this entire ICH 8 has been divided into 4 parts: 18, 90, 20, 21. So we go and see page number 18. You see, this is PCI part. You can see over here in the block diagram, we have a PCI interface. Now you see over here, let's go to the next page. Let's go to the next page and we find more things, right? You see RTC section, you will find here also the RTC section. RTC, you see RTC. Now you see LPC, you will find over here LPC. You see LPC interface. So nothing is outside of this data sheet. So what is important is to understand this data sheet, right? To understand this data sheet, and we can see anything in this schematic diagram. You see CPU interface. You can see over here processor interface. What are the signals? A20M, FERR, IGNNE, INIT, RC. You can see over here in a schematic. IGNNE, INIT, A20M, all those same signals, right? So what is important? Important is to understand the data sheet, because any manufacturer will implement this thing, right? Will implement this thing. So we are already gone through the block diagram. Now So what is the first thing? First thing is to understand features. Second thing is to look into the block diagrams. Now third thing is to look the configuration. We can see the configuration. This is for ICH9. If it is used in desktop, how ICH9 will be used, and you see here ICH9 when used in notebook, that is ICH9 will be connected through GMCH via DMI. It is managing the power management, it is clock generator, then SM bus, PCI bus, LPC bus. You see LPC bus, it is connected to IO controller and PCI Express. So this is the configuration, how the ICH9 would be connected in notebook motherboard. What parts would be connected in ICH9, right? What parts should be connected in ICH9? And you can see in the block diagram, usually you see the block diagram, the various parts connected are governed from here, from this point. So now we have seen the mobile configuration. Now what is most important is go through page number 108. Kindly note what pages I am seeing, because I am going to see this same conceptual system block diagram while discussing Intel Series 5 chipset, also Intel Series 6 chipsets. This data sheet is having 884 pages. I'm not going to discuss 884 pages. What I'm going to discuss is most important pages. So what are most important pages? First is features page, right? Second is configuration page, right? Third is system block diagram, and the fourth is the conceptual system clock diagram. We are going to discuss how clock is distributed. Now you see ICH9 requires an external clock generator. And what are the important signals? The clock generator will generate 33 megahertz, 14.318 megahertz, 48 megahertz, all to the ICH9, and PCI clock and a signal, stop CPU, a stop PCI will come over here, and you can see this sus clock 32 kilohertz. We'll discuss about the sus clock. You can also see in the diagram of clock generator. Let's see where is clock generator, page number 3rd, and you can see the page number 3rd, and you can see in the data sheet 33 megahertz. We'll find over here, we'll find in the data sheet 33 megahertz, right? The 33 megahertz is generated. Then you can see 48 megahertz. You see 48 megahertz, then 14.318 megahertz. Three frequency to ICH9, right? 3 frequency. You can see over here 48 megahertz, right? Then you can see this reference clock peg underscore ref CLK, peg underscore ref clock positive and clock negative. This is 14.318 megahertz. This frequency feedback to the PCH. You can search over here PEG underscore REFCLKP. You see, this is sent back to the ICH, right? So anything is governed by the data sheet. So when we are discussing about the clock, what important clocks are generated, we have to see this diagram, and in this diagram we can see this 3, and you can see 2 important signals coming out from ICH to clock generator. What are those? Stop underscore CPU and stop underscore PCI. We'll also understand what is the meaning of these 2 signals, but meanwhile we'll check over here. In a schematic diagram, you see STP underscore CPU, and where this signal is coming, you see the signal is coming out from your ICH. So how these are governed? It is governed through this data sheet. So you have to see the data sheet, right? Now we are going to page number. Now this important block diagrams have been cleared. Now for diagnostic point of view, now from diagnostic point of view, what is important now? To check the power sequence, to check the power sequence. So we'll go to 325, and here is our power sequence. You see, basically this is the power sequence. First step, second step, third step, fourth step, fifth, sixth, seventh. This is the correct power sequence. And while checking this sequence, if you check this sequence step by step, I am 110% sure you are going to find out the faulty parts in your notebook motherboard. Always follow the power sequence mentioned in the data sheet. Always follow the power sequence mentioned in the data sheet, and if you follow each of the steps, you are going to find out the faulty parts. And we are going to describe this sequence now, and you can see how everything is covered. Every power supply has been covered in this sequence. Okay, so now we see the power sequence, right? Now you can see in this data sheet the power sequence is starting from VCC RTC, right? So we go into this schematic diagram and we see what is VCC RTC. VCC RTC is our supply, that is RTC VCC, right? You can search over here, VCC RTC, and you can see this VCC RTC is connected to plus RTC VCC. So I am telling you to start testing notebook motherboard from this point, VCC RTC. First you have to check whether VCC RTC is there or not. Now my VCC RTC is connected to plus RTC VCC. I'm not telling you to start checking from adapter, no. Start checking from VCC RTC, because this is the first step. You can see in the data sheet VCC RTC is the first voltage, right? First voltage. So we go in the schematic diagram, we have searched exactly VCC RTC and it is connected to plus RTC VCC. Now we'll see from where this RTC VCC is coming. Kindly note, whatever your diagnostic way may be, whatever you are currently doing it, just go through my steps and you will find that you will miss nothing. You will miss nothing in between while testing by this way. So now we search, we have checked. Now we are going to measure VCC RTC. So VCC RTC is connected to plus RTC VCC. So we search from here. Now we'll see, yeah, now your plus RTC VCC is generated in two ways. One through 3D3V underscore AUX underscore S5 or through RTC battery. Sometime when your RTC battery is faulty, then this RTC VCC won't be generated and hence your notebook motherboard won't turn up. So always start from VCC RTC. So what we have done is we have searched VCC RTC and VCC RTC is connected to plus RTC VCC. So we'll find where this plus RTC VCC is there. Now we we find that this RTC VCC is connected with this thing. Suppose your RTC VCC is missing, then in that case what component can be faulty? This capacitor can be faulty, or this general diode can be faulty, or this voltage is missing, or this RTC or this battery is faulty, or the connector is faulty, right? So always start from here. Now you can see this RTC VCC is fed by 3D3V underscore AUX S5. Now we'll find from where this 3D3V underscore AUX underscore S5 is coming, right? Wait, sorry, we'll write 3 over here. Sorry. What we are started with? VCC RTC. VCC RTC is connected to plus RTC VCC. So we'll find RTC VCC, and this RTC VCC is connected from here. Suppose in this case it is missing, we have to check this capacitor, this resistor, we have to check whether it is coming or not. So for checking it, we'll find from which place it is coming, right? From which, suppose this is not coming, suppose this 3.3 volt is not coming over here. So now we'll find from where this is coming. We already know it is coming from 3.3 volt, 3 volt, 5 volt regulator, right? 3D3V underscore AUX underscore S5. So now we locate this thing. So always start, you can see this 3D3V underscore AUX S5 is generated via this V regulated 3. This is the LDO voltages. So if this LDO voltage not coming, then we have to check this. Then we have to check this 3 volt 5 volt regulator, right? Now you come back over here. We had already discussed about this 3 volt 5 volt regulator in earlier classes. So what I did was, I did not started with testing adapter voltages and then measuring 3 volt over here. What I did was, I started with the sequence that is mentioned in the data sheet. And what is the sequence mentioned? Start with VCC RTC. So while checking VCC RTC, we have come back at 3 volt 5 volt regulator, but in between we had checked many things, like you see plus RTC VCC. We go to plus RTC VCC, TC VCC, and we find this is generated. Many people miss this thing. Sometimes this capacitor is faulty, this resistor is faulty, then even though your board won't turn up. And what people used to do at that point of time, they used to change 3 volt 5 volt regulator, they used to change IO controller, but the fault is in very first step. So my first step is VCC RTC. Now we go to our data sheet. Follow this procedure of testing boards, right? I'm talking about ICH9. So we go to see the next signal, and what is my next signal? My next signal is RTC reset hash. So we'll find over here in our data sheet RTC RST hash. Yes, and this is connected to plus RTC VCC. Meanwhile, we'll go in our presentation and find the description of this voltage. What is VCC RTC? VCC RTC is 3.3 volt supply for RTC well. So this ICH9, it has one RTC well, and this 3.3 volt is the supply. This is the starting point. This is the starting point, and you can see this power is not expected to be shut off unless the RTC battery is removed or completely drained. So my first step is to check VCC RTC. What is my next step? I am not talking anything in air. It is already mentioned as data sheet. So this is the correct power sequence. This is the correct power sequence, and while following this power sequence, you can check entire notebook motherboard, and you can find even the minus, even the tiniest of problems in your notebook motherboard if you follow this procedure. If you follow this procedure, you see how checking VCC RTC, we go back to check the 3 volt 5 volt regulator, right? So now my second is RTC reset hash. So first we'll understand the meaning of this signal. RTC reset hash, when asserted, this signal reset register bits in the RTC well, and RTC reset input must always be high. It is clearly mentioned in the data sheet that RTC reset hash input must always be high. As I have already told you that hash means it becomes active when this signal is low, but it should remain always at high, and high means it is connected to 3 volt. You can see 3 volt. And the third thing is ICH INT VRMEN. What is VRMEN? Internal voltage regulator enable, and this internal voltage regulator enable is connected to 3 volt. So this signal is active, as we had already discussed in our features. You see, in our features page we had already discussed. And where is our features page? We'll go to page number 40, and you see in our features page, you will find it supports 5 integrated voltage regulators. Now this 5 integrated voltage regulators are enabled. These are enabled via this signal INTVRMEN, internal voltage regulator enable, and this is connected to RTC VCC. So all the 5 internal voltage regulator are enabled during a startup. So what we have discussed till now? Let's go back at our power sequence page, and our power sequence page is at page number 325 and 326. So VCC RTC, we have checked the first signal VCC RTC. This VCC RTC is fed in our schematic diagram via, you see, once again we'll revise this thing. We'll keep revising this thing, and we have to follow this procedure of testing notebook motherboard. Yes, this is the best way, and this is the best way to test any notebook motherboard. So we have to check VCC RTC. Now I know VCC RTC is fed through plus RTC VCC. Now we have to check where this RTC VCC is coming. Plus RTC VCC. This is coming from this supply or this battery supply. If this is missing, then what can happen? Either these two are missing or these two components are faulty. So we have to now check this signal. So we go and check 3D3V underscore AUX underscore S5, right? And we find where it is coming from. Where it is coming from? It will come from the 3 volt 5 volt regulator IC, and we can see, yes, this is coming from V regulated 3. So if this is missing, then what we have to check? We have to check this regulator. then this regulator input may be faulty. What is the input? We had already discussed. Input is V in DC bat out. So now we have to check whether DC bat out is coming or not. We had already discussed in our previous class how this DC bat out and V in is generated, right? So in that case we have to find whether DC bat out is coming or not. If DC bat out is coming and this is not generated, this is LDO voltage, then this IC is faulty, right? Now we will change this IC. This is the correct sequence, right? No, if we don't know the correct sequence, then we can take a lot of time in repairing a board. But if we know the correct sequence, the correct procedure, we can repair the board easily and with lesser components, right? With lesser components. So now I go to this back to the data sheet and see RTC RST has, as I have already seen, RTC RST has. You see RTC RST has. You see each one of them has timing, right? First VCC RTC, then RTC RST, right? So we'll see where is RTC RST. It is connected with plus RTC VCC, right? So this should always be high. We had already discussed what is the meaning of this, and we have to check this INT VRMEN. What is INT VRMEN? Internal voltage regulator enable. And as I have seen in the features page, it has 5 voltage regulators, internal voltage regulators. So these 5 internal voltage regulators will be enabled over here. Now you got my point. Why I am telling you to remember all the things which I had spoken, because all of them are correlated. All of them are correlated, right? Now we go to see our next signals, and our next signal is V5RE.
And this is Vikas from Tronik, and today I and my colleague Mr. Nitin will take over this class, and this class is about VGA complete process, VGA rework complete cycle, and there are various steps in a VGA rework. But before starting with this process, I will first discuss about the types of VGA machine and what are the different consumables and spare parts, spare accessories that are needed while doing a VGA. In the market there are different types of VGA machine, and people often get confused on which machine to choose. So, but if you are concerned about only notebook motherboard, I would suggest you to go for a VGA machine which is mixed technology, that is both hot air and IR technology. But if you are only interested in doing a smaller PCB like mobile phones, and you are concerned about removing plastic components, then you can go for IR machines. And there are various models, popular models in this series. In hot air models, DHC1, this is very quite famous model across the world, and there are various versions of this machine which are popular by name of like 5860 and 5830, but the machine is same and the basic feature set in the machine is same. So you can see in this machine, this is having 8 heaters all heating in X, Y, Z direction. That is, you can see there are 2 left heaters, 2 right heaters, and you can see this is one X in Y direction. There are 2 heaters. These all 6 heaters are IR heaters, and very good technology IR heaters, both all made from L steel. And these are 2 hot air heaters. In some machine you may not find this bottom heaters, so I suggest you to discard those models which do not have this bottom heaters, because this is very essential. And one more thing is that this bottom heater must move up and down. Similarly, this top heater should move in all 3 directions, that is, you can see X, Y, top and bottom, and you can see this direction. So X, Y and Z, all these 3 movement should be there in your top heaters. And this machine also have one lamp for visual inspection. This is Cobra LED light, commonly technical term is Cobra LED light, and will enter into the machine. This is having a touch panel, that is MCGS touch panel. If some models will look similar to this machine, but if they lack in this touch screen, then again I suggest you to discard those models, because you need to save various kind of profiles in the machine. Because not every time if you are doing a BGA, you don't have to select temperatures every time. You have to just save one profile and select profiles. So we'll also discuss how to create profiles while doing all the steps. And in this machine, a very important feature is that this machine is built with 3 internal thermocouplers. You can see the one thermocoupler is in the bottom heaters to sense the temperature of bottom heaters. Similarly, there is one thermocoupler over here to sense the temperature of higher heaters, and there is one thermocoupler inside the top heaters. So there are 3 inbuilt thermocouplers, whereas you can use one K-type thermocoupler to sense the temperature of PCB, but it is hardly required when you are using a hot air BGA machine, whereas if you are using a IR BGA machine, then it works solely on this K-type thermocoupler. So, and this machine is inbuilt with a vacuum pump, and you can see if you press over here, this vacuum pump will work, and we can see the capability of this vacuum pump. You can put over here, and you see it can pick like this. So it has great strength. It can pick a BGA chip from a board. Similarly, you can see if you press cooling, then you can see there is air blowing from the fan, and we can see we can see in the interface there are various kind of menu buttons. So we'll understand what are the function of each of the buttons. Before I describe this interface, I'll also tell you about the PCB support capability of this machine. This machine can support various kind of boards via these hangers, or which may be called as PCB supporters, and the machine which do not have this facility that may cause problem of board bending, right? Board bending. So this machine can support various kind of PCB board, irregular kind of PCB boards, and one very good feature of this machine is that we can control these side heaters. Suppose your PCB only fits from here to here, then there is no need of using these side heaters. We can turn off these side heaters via these side switches. So in that case we can save some energy, right? We can save some energy. And in the interface you can see first button is start. When you press this start, then this machine will get start right now, and this button you can see, this button shows the status of BGA machine. Right now this machine is not started, so it is in a standby condition. When we press this start, you can see it starts heating up. Now we want to stop this BGA machine, then we can press stop, and you can see it's now back into standby condition. And another button is cooling. If you press cooling, then you can see there is a fan. The fan has started blowing air, right? The fan has started blowing air. Similarly, we have a button vacuum. When you press vacuum, then your vacuum pump gets started, and you can feel the power of this vacuum pump. And you can see, we can pick up this desoldering wire via this vacuum picker. So it has an excellent capacity to press to pick up a BGA chip. and now we can see there are on the side there is temperature showing up. This is first, second, third and fourth. This outside is for you. If you install a K-type thermocoupler over here, then this outside will show the temperature of PCB, whereas this upper it is showing the temperature of the top heater, and the lower it is showing the temperature of the lower heater, whereas this infrared is showing the temperature of this side heaters. And this side heaters is not mandatory to use. We can also turn off this side heaters, and it depends which kind of board we are having, so that we can turn on these side heaters. So, and now we'll go into the program selection, and you can see in the program selection there is a name. You can go into selection, then there are two inbuilt profiles which we have saved in this machine. Suppose we select PCH, we'll also discuss how to design a new profile, and you just press apply and we can press start, then this machine will be started. So we have understood the basic functions of all the various parts in this machine. Now we'll discuss about the consumables, because in order to do a BGA process perfectly, you have to have two things. One is correct type of BGA machine, and the more important than BGA machine is to have better consumables. So we'll discuss about the consumables while doing a BGA rework. And what are the consumables? You will require good quality of solder balls, lead free solder balls preferably. If you have lead free solder balls, then those are preferred, and a very good quality of BGA flux. In market you may find Kingbo BGA flux, but there are many fake, and how to identify which is good quality BGA Kingbo BGA flux is by seeing the color of BGA flux. If that is white in color, then that BGA flux is better, whereas yellow one is not good. And this machine will have various type of nozzles according to the type of BGA chip we are trying to remove. You can see these are removable. There are three types of there are basically 5 types of nozzles, 2 for the bottom. You can see there is a hole inside this nozzle to support air flow, right? And it has a supporter over here, because this supporter will give support to the PCB from the bottom side. And there are 3 types of nozzles for the top heaters. If you have some specific designs, like if you want to remove RAM slot or some other kind of BGA chip, then that can be custom designed. These nozzles can be custom designed for that process. But mostly for notebook motherboards, these three kind of nozzles for top heater is okay. And we have apart from solder balls, you require stencil set for making balls, and there are 2 types of stencil set in the market. One is direct hit stencil set, one having size of 80 by 80 mm. This is smaller in size, but that is direct hit. Direct hit means you can put hit directly on this stencil and it won't bend up. And there is one more type of direct, this is indirect, non-direct hit stencil set. This stencil set and jig is used by beginners, one who is beginning with BGA process, then they can use this non-direct hit stencil. This is the stencil and this is the jig for the non-direct hit stencil. Whereas for direct hit, we have a very simple stand for direct hit stencil, and you can start using this from initially also, but you require some practice while using direct hit stencil. But once you gain practice, then this is better than non-direct hit. And for board cleaning, we require a very good quality desoldering wire, and I would suggest you to go for good brand. That is because this is very good quality of desoldering wire. and we'd also require thinner, a very good quality of thinner. There must be right mix of alcohol in this thinner to use it on the PCB board. This is for cleaning the PCB, and we'd also require a very good quality of soldering iron. So as I said, there are many steps in a BGA rework cycle, and my colleague Mr. Bipin will start with these steps. The first step in a BGA cycle is first to preheat the board. We have to preheat the board for around 12 hours before doing BGA. Before removing BGA, we have to bake that PCB for 12 hours at around 125 degrees Celsius, and that is the first step. So we are going to use a first step, and this is our board. We are going to remove the BGA chip on this board, and we're going to also test whether our BGA is successful or not. So we'll start with the first process. First to bake this PCB for 12 hours, and then the second step is to remove the BGA with the BGA machine, and the third step is to clean this PCB. Fourth step is to make new balls on this new balls of this BGA using this directed stencil set through these solder balls and BGA flux. And the next step is to resolder this BGA chip, and the next step is to inspect this PCB whether this BGA has been done correctly or not. So now we are going to start with the first process. We can see in the interface there are various kind of menu buttons, so we'll understand what are the function of each of the buttons. Before I describe this interface, I'll also tell you about the PCB support capability of this machine. This machine can support various kind of boards via these hangers, or which may be called as PCB supporters, and the machine which do not have this facility that may cause problem of board bending, right? Board bending. So this machine can support various kind of PCB board, irregular kind of PCB boards, and one very good feature of this machine is that we can control these side heaters. Suppose your PCB only fits from here to here, then there is no need of using these side heaters. We can turn off these side heaters via these side switches. So in that case we can save some energy, right? We can save some energy. And in the interface you can see first button is start. When you press this start, then this machine will get start right now, and this button you can see, this button shows the status of BGA machine. Right now this machine is not started, so it is in a standby condition. When we press this start, you can see it starts heating up. Now we want to stop this BGA machine, then we can press stop, and you can see it's now back into standby condition. And another button is cooling. If you press cooling, then you can see there is a fan. The fan has started blowing air, right? The fan has started blowing air. Similarly, we have a button vacuum. When you press vacuum, then your vacuum pump gets started, and you can feel the power of this vacuum pump. And you can see we can pick up this desoldering wire via this vacuum picker. So it has an excellent capacity to press to pick up a BGA chip. And now we can see there are on the side there is a temperature showing up. This is first, second, third and fourth. This outside is for you. If you install a K-type thermocouple over here, then this outside will show the temperature of PCB, whereas this upper it is showing the temperature of the top heater, and the lower it is showing the temperature of the lower heater, whereas this infrared is showing the temperature of this side heaters. And this this side heaters is not mandatory to use. We can also turn off this side heaters, and it depends which kind of board we are having, so that we can turn on these side heaters. So, and now we'll go into the program selection, and you can see in the program selection there is a name. You can go into selection, then there are two inbuilt profiles which we have saved in this machine. Suppose we select PCH, we'll also discuss how to design a new profile, and you just press apply and we can press start, then this machine will be started. So we have understood the basic functions of all the various parts in this machine. Now we'll discuss about the consumables, because in order to do a BGA process perfectly, you have to have two things. One is correct type of BGA machine, and the more important than BGA machine is to have better consumables. So we'll discuss about the consumables while doing a BGA rework. And what are the consumables? You will require good quality of solder balls, lead free solder balls preferably. If you have lead free solder balls, then those are preferred, and a very good quality of BGA flux. In market you may find Kingbo BGA flux, but there are many fake, and how to identify which is good quality BGA, Kingbo BGA flux, is by seeing the color of BGA flux. If that is white in color, then that BGA flux is better, whereas yellow one is not good. And this machine will have various type of nozzles according to the type of BGA chip we are trying to remove. You can see these are removable. There are three types of there are basically 5 types of nozzles, 2 for the bottom. You can see there is a hole inside this nozzle to support air flow, right? And it has a supporter over here, because this supporter will give support to the PCB from the bottom side. And there are 3 types of nozzles for the top heaters. If you have some specific designs, like if you want to remove RAM slot or some other kind of BGA chip, then that can be custom designed. These nozzles can be custom designed for that process. But mostly for notebook motherboards, these three kind of nozzles for a top heater is okay. And we have apart from solder balls, you require stencil set for making balls, and there are 2 types of stencil set in the market. One is direct hit stencil set, one having size of 80 by 80 mm. This is smaller in size, but that is direct hit. Direct hit means you can put hit directly on this stencil and it won't bend up. And there is one more type of direct, this is indirect, non-direct hit stencil set. This stencil set and jig is used by beginners, one who is beginning with BGA process. Then they can use this non-direct hit stencil. This is the stencil and this is the jig for the non-direct hit stencil. Whereas for direct hit, we have a very simple stand for direct hit stencil, and you can start using this from initially also, but you require some practice while using direct hit stencil. But once you gain practice, then this is better than non-direct hit. And for board cleaning, we require a very good quality desoldering wire, and I would suggest you to go for good brand. That is because this is very good quality of desoldering wire. And we also require thinner, a very good quality of thinner. There must be right mix of alcohol in this thinner to use it on the PCB board. This is for cleaning the PCB. And we also require a very good quality of soldering iron. So as I said, there are many steps in a BGA rework cycle, and my colleague Mr. Bipin will start with these steps. The first step in a BGA cycle is first to preheat the board. We have to preheat the board for around 12 hours before doing BGA. Before removing BGA, we have to bake that PCB for 12 hours at around 125 degrees Celsius, and that is the first step. So we are going to use a first step, and this is our board. We are going to remove the BGA chip on this board, and we're going to also test whether our BGA is successful or not. So we'll start with the first process. First, to bake this PCB for 12 hours, and then the second step is to remove the BGA with the BGA machine, and the third step is to clean this PCB. Fourth step is to make new balls on this new balls of this BGA using this directed stencil set through this solder balls and BGA flux. And the next step is to resolder this BGA chip, and the next step is to inspect this PCB whether this BGA has been done correctly or not. So now we are going to start with the first process. Okay, now we have finished up with our step 1, that is we have baked this board for around 12 hours at 125 degrees Celsius, and now we have put up the board back onto the BGA machine, and you can see how we have fixed this board on the PCB on the BGA machine using the PCB supporters. It must not be loose. You can see all this is firmly set up on the BGA machine. And now we will put the bottom heater down to start with our BGA process. But before we put the bottom heater down, we'll apply BGA flux gently on the board. Yes, little flux only all across the border of BGA chip. Yes, little flux around the corners of BGA chip, the BGA chip which we have to remove. Now we'll put the bottom heater down, and you can see we'll go in our interface of BGA machine, and we've also used a protective aluminum tape across the BGA chip to prevent burning of components, right? So you can use two kind of tape. You can use aluminum tape or Kapton tape. Also beneath the PCB, you can use the Kapton tape to prevent the resistors below the PCB, right? So now we'll go into the interface of our BGA machine. We'll go to the program selection, and we have already set up this profile, PCH profile. We'll confirm, and you can see there are various steps. Step 1, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, and the temperature value will change according to the type of BGA chip we are removing, because various kind of BGA chip have different solder ball size, and the number of solder balls also changes. So we have to change this temperature according to the type of BGA chip we are removing. Right now for this BGA chip we have made a profile up to 5th step, and suppose you are playing with your BGA machine, then you might at some time go to 6th step or 7th step. But this profile is exact profile that we have made for a BGA chip that we are going to remove. And here you can see this is upper temperature, lower temperature, and infrared temperature, and this is the rate at which the temperature will increase. Basically this BGA machine has an PID controller. PID controller will reach to this value of 150 from 185 via this rate. So that rate is the increasing temperature value, how much the temperature will increase. Now we'll start the profile. We'll first apply, and now we'll start it. And you can see this BGA machine will work. It will give a beep sound, and when before giving that beep sound, we have to just that this vacuum pan will automatically turn on, and we have to pick that BGA chip. So we'll wait for the process. Right now this is in heating stage. And you can see the various thermocoupler are working and they are increasing the temperature. You can see the temperatures over here. We are not using an external K-type to measure the PCB temperature. That is not necessary. So it is at default value. And you can see all these three are changing, and right now this is in heating stage. So we'll wait for the profile to get complete. And you have to change the profiles according to the type of BGA chip you want to remove. So if you need help in making profiles, you can always contact us. You can go in screenshot and you can take a screenshot of this profile, right? So if you are having problem with your BGA, then I can always take a screenshot and send to you. We'll also cover in our class the various stages in BGA process. Basically there are three stages. This stage is called preheat stage, this is reflow stage, and the last soak phase, and the last is cooling phase. So there are basically four phases in the BGA rework cycle. One, preheat, where the entire board is preheated. Then reflow, that is the temperature is ramped up, and the soak phase, when the ball gets melted. And you can see this is the time being shown over here, right? And this is the heating time. You can see 147 seconds total time that it has taken till now. And you can see we have already put this value in our profiles, 25 seconds, 30 seconds that we have put up in our profiles. This is the temperature constant time that is showing up. And when it will reach the final stage, a beep sound will come and your vacuum picker will automatically turn up, and then we have to remove the BGA chip with that vacuum pen. Sound has already come. Now the vacuum picker will automatically turn up, and you can see we have removed the BGA chip successfully without any manual intervention. You see, without any manual intervention, and your fan is automatically turned up, and you can see this cooling. This cooling is automatically turned up, and now we'll cool this board. And the next step is to clean the PCB and to clean the BGA chip. Okay, we'll start with the second step, the next step, that is cleaning the PCB. You can see we have removed the BGA chip from this machine, from the BGA machine, and you can see there is no board bending problem. So that means we have a very good BGA machine over here, and you can see all components are there on the back side of the PCB. Now what we'll do is we'll clean this PCB, but before cleaning we'll apply little flux over here, and now we'll start cleaning this board. Board cleaning is a very important step. Even if you have costliest of BGA machine, but you won't do this board cleaning properly, then your BGA process will be a failure. So what we have to do, we have to clean the board properly we do not have to leave any residue on the board. That is very important, right? That is very important. And for board cleaning, we can use a very good quality of solder iron, a branded solder iron, and you can also use some edge type solder bits, but we are using it with a normal one. That is also good. But what is important is a very good quality of solder iron, preferably 50 to 60 watt of solder iron, and a very good quality of desoldering wire, because that is very important. And you see we won't leave any residue on the board. That is very important, because it will have corrosion on the PCB, and that may lead to short circuit, internal short circuit. So when you place a new BGA chip over here, then even though that won't be successful, because we have not cleaned the board properly. So what we need is to gently clean this BGA area, right? You can see we are cleaning it very smoothly. You should not be hard on the track, on the pads, because that may damage the pad, and that's why this is a very essential part, very essential step, and it has to be done smoothly. You have to practice a number of times in order to achieve efficiency in this step, and this step is very important. You can see we have cleaned all the pads, all the BGA pads, and we'll clean it up. Now we'll remove it. So we'll remove it through brush using thinner. You can see we are using thinner to clean this. Yes, we wash the pads through thinner this way. Yes, it has to be done firmly, like this way. This step is very important, and we need to practice this, because you see the first two steps has done by machine, whereas this step is done manually. So here we require practice, and we have cleaned the board properly. Now our next step is to make balls on the BGA chip. We'll clean the BGA chip and we'll make balls using direct heat stencil. Okay, so we'll now move to the next step.
So let's start BGA reballing process now. Apply flux on it. And then gently clean this IC. After cleaning with thinner. Here we use direct heat stencil. This is direct heat stencil stand. Again we apply little flux on it. And then fix this IC onto the stencil. Now align this IC okay. Now on the stencil ball size are written on it. Now here stencil ball size is written 0.5, that's why we use 0.5 ball. Okay, now here we go. Give heat on the IC. Before removing stencil, you check your balls is set on the IC or not. If some balls is not fixed, you give heat again on the IC. Check it again. Little one ball is remaining, so we give more heat. Okay. Now we remove this stencil. Okay. Now check, reballing process is finished.
Now you can see after reballing, you can see how cleanly we have made balls on the BGA chip, and this is very important. In order to do reballing, you have to make balls properly, and we have used direct heat exchanger to create balls over here. And now we'll apply little flux over here on the pads, and then we'll align this BGA chip onto the PCB, and we'll do the same process, the process that we have used to remove the BGA chip. And you see the balls should be made very cleanly. You see there is no disorientation of balls, and this is very important. So before putting BGA chip onto the PCB, you have to inspect these balls, whether these balls are correctly aligned or not. So reballing is very essential. Now we'll apply a little flux over the pads, and we'll align the BGA chip over here. And after our alignment process is done, we'll use the machine. Some BGA machines have inbuilt CCD camera in order to do this alignment process, but those kind of BGA machine are a little bit costly. So if you have budget, then you can go for an alignment kind of BGA machine, and but if you don't have budget, you can use it manually also, right? You can align this BGA chip manually also. We'll show you how to align it. Now you can see we have aligned the BGA chip after revolving over here onto the PCB, and what we have done is how to check whether your BGA chip has aligned properly or not. You have to see the borders from all the four sides onto the PCB. You can see all the borders should be visible after placing the BGA chip, and also there is a marking on the BGA chip while on the PCB, that is which way to orient the BGA chip, how to place the BGA chip. Sometimes there is a confusion how to orient this BGA chip, and we can clear this confusion by seeing a marking onto the PCB. There is small marking on the PCB, whereas there is marking on the PCB as well as on the BGA chip, and both the markings should be in the same direction. That is the way to orient the BGA chip. And how to check alignment? We have to check alignment by seeing the borders from all the four sides, and all the borders should be visible. If all the four borders are visible, then we can think that this BGA chip has been correctly aligned. Now what we'll do is we'll start our BGA machine. We'll follow the same procedure to heat this, to resolder this BGA chip back to the PCB. Okay, now we have placed the BGA chip onto the PCB. We'll put down the top heater, okay, just above the BGA chip, and we'll use the same profile that we have used for desoldering the BGA chip. You can see in the program selection, it should be in selection PCH, confirm, apply, and we'll start. And you can see the same process which we have followed for desoldering BGA chip is used for soldering BGA chip back to the PCB. And we'll wait for the BGA machine to finish it up, finish the process. Yeah, and we'll wait for the profile to end up. After the profile ends, we have to wait for 10 minutes for cooling, for getting the PCB cooled. And you can see how the smooth is while using a touch screen based BGA machine, because it clearly shows the various temperatures and the curves and the correct current stage of the BGA machine. That is very important. Nowadays this kind of BGA machines are very cheap, but what we have to concern about is good quality heaters and good quality of software, and this PCB support is very essential. After soldering back the BGA chip, we'll inspect this PCB and we'll test whether this process has been okay or not. So it takes close to about 150 to 200 seconds to complete this process. So close to it. You can see there is a time step second 250 seconds over here. So, and the total second will be here approximately 250. Now it has crossed 155 seconds. So you can see there is a ramp of temperature, and the lower heater temperature you can see is higher than the lower heater, and upper heater are close, where the higher heater temperature is lesser than the top and bottom heater. So the heater which participate in this work are mostly top heater and the bottom heater, while the side heater is for maintaining equilibrium on the board. You know, PCB equilibrium. If you do not heat, then it will get bent. See, the temperature is 168 seconds for the higher heaters. You can see over here. And if you touch over here, it will show you the temperature 238, and close here 258. You can see the temperature that is currently running onto the BGA machine. And now the infrared temperature is 165 and the beep sound has come up. So we don't have to do anything, we have to just wait for 10 minutes after finishing up this profile, and then we can remove the PCB back and we can test and inspect this. You can see how smoothly we have fixed the BGA chip onto the PCB, and you can see there is no trace mark on the PCB. We have cleaned the PCB properly. So this is the process by which you have to do BGA revolving. Now what we'll do is we'll test this board with the screen. We'll attach the display cable to the PCB, and we'll also attach the adapter to the DC socket. And now you can see we'll press the button. See, yeah, this board is having a display, a little bit of, yes, you can see this board is working perfectly. So that means our BGA process has been complete without any failure, and the complete success of BGA depends on, as I've already told you, depends on two things. First, using a correct BGA machine, and second, the manual process that we have used, board cleaning, making balls, no trace marks on the PCB. That is very important. And if you follow these steps, then you can also give warranty on BGA revolving. Customers often ask how much warranty you give on BGA revolving, but if you follow the correct procedure, then you can give warranty on BGA revolving. Now our whole process is complete, and in the next class we'll cover another practical session on some different device. So thank you.
3 V underscore AUX underscore S5 is connected to V regulated 3, that is the LDO voltage of 3 volt 5 volt regulator IC. So let's consider a case that this 3.3 volt auxiliary always on, this is also called 3.3 always on, is not coming. Then in that case what we have to check? We have to check V in, that is DC bat out. If this IC is having V in and this LDO is not coming, then what can be the problem? The problem would be in the IC itself, right? The problem would be in the IC itself. The problem would be in the IC. So we have to check V in, and if this 3D3AUX S5 is not coming and your V in is not coming, that is DC bat out is not coming. So what we have to check? From where this DC bat out is coming? DC bat out, right? So we go and check from where this DC bat out is coming, and you can see the DC bat out is here from adapter volt to DC bat out, and in this case we have to test for this MOSFET and we have to check this charger IC, right? So eventually if your problem isn't DC bat out, you will come to this place after checking VCC RTC. So for testing VCC RTC we have come to the place of checking, DC bat out. You can see the whole relationship. So always follow the sequence that is mentioned in data sheets, because if VCC RTC is not coming, then we are going to find out checking DC bat out. In that case, every important thing that is related to VCC RTC we could have checked, right? And if you do not follow the correct procedure, we may overlook some components which may be faulty, and we cannot find those small components if we cannot follow the correct procedure, right? This is, you can call it as a simple process to test notebook motherboard, right? So we have reached up to the place where if suppose DC bat out is not coming, then in that case we will check for this MOSFET, we will check for this charger IC, that is we will check for PDS, PDL, pull down source, pull down load. We have already discussed in our earlier classes. Now we are using those concepts to study over here. So if DC bat out not coming, then we have to check for this MOSFET, we have to check for this charger IC. So you will come at the correct place, right? Now our next signal is RTC reset hash, and we can see also over here the explanation of these signals. This is written as also will just read about the explanation of VCC RTC. What exactly VCC RTC is? This is the supply for the RTC well. Basically, any ICH or PCH, the Intel has divided the power for this. Basically, this ICH and PCH are made up of very small internal MOSFETs, right? This is a big chip having a lot of MOSFET inside this processor with logic inside it. So we have divided the power for this chipset into various well, that is RTC well, sleep well and core well. So VCC RTC is the supply for the RTC well, and this should be always turned on, right? This voltage should always be there. An RTC reset, when asserted, this signal reset register bits in the RTC well. So the RTC reset input must always be high. So we'll go in a schematic diagram this RTC reset signal from where this is coming. So we'll just search RTC reset. RTC reset has, and you can see this, since it is written this RTC reset should always be turned high, because low will activate this RTC reset and that will reset the register bits in the RTC well. So this RTC reset will go and see over here, this RTC reset should always be connected to high, that is 3.3 volt. So this RTC reset is already connected to plus RTC VCC. So we have already traced how this RTC VCC is generated, right? Now we move to the next signal, and our next signal is V5 REF underscore sus, right? V5 REF under reference, V5 reference underscore sus. So let us first understand what this volt means. This volt is reference for 5 volt tolerance on suspend well inputs, and this is connected to 5V underscore S5. So we can go and check in a schematic diagram our signal name, and our signal name is V5 REF sus. So we just go and see where this signal is coming, V5 REF sus, and you can see V5 REF sus, all those signal mentioned in the data sheet would refer to the name inside the chipset. You can see V5 REF underscore sus name is inside the chipset, where outside the chipset the name has changed. It is ICH underscore V5 REF sus. So this V5 REF sus is connected to, you can see it is connected to 5 volt underscore S5. Now we'll check from where this 5 volt underscore S5 is coming, right? 5 volt underscore S5, and we will check from where this 5 volt underscore S5 is coming, right? Wait, yes, and you can see this 5 volt underscore S5, 5 volt underscore S5 is being generated from 5V underscore AUX underscore S5, right? AUX underscore S5. And how it is generated? This is generated via PWR S5 underscore enable, and where this signal is coming, we'll search, right? From where this signal is coming, right? And you can see this signal is coming from this signal AB. This is small IC, this is AND gate. This you can see AB will give Y, and what is A? A is EC underscore RST. So we have to check EC underscore RST, right? And EC underscore RST is input of, what is? It is input of IO controller. So we'll go and see EC reset, right? EC RST has, right? And you can see this EC reset is going to the input pin of IO controller also. And from where this EC reset is coming? This EC reset is basically coming from this 3D3. It has been taken from 3.3 always on voltages and it will be given to the IO controller. And this S5 underscore enable, this will go, it will come from IO controller, right? It it will come from IO controller. We have to just see yes, S5 underscore enable. So that means this signal V5 ref underscore sus will get generated. V5 ref underscore sus will get generated only when we will go and see again. V5 ref underscore sus will get, this is connected to 5v underscore s5, right? 5v underscore s5. So this 5v, how this 5v underscore, suppose this V5 ref sus you are not getting. If you are not getting this volt, so what would you trace? We'll go and find out 5v underscore s5. Now this 5v underscore s5 is being generated from 5v underscore aux underscore s5, and this is coming from the 3 volt 5 volt regulator. This is LDO voltage of 3, this is LDO output of 3 volt 5 volt regulator, right? So if this is not coming, then you have to check the DC bat out and the 3 volt 5 volt regulator IC. If this is here and this is not coming, we have to check for this MOSFET, right? This is a P channel MOSFET, right? This is a P channel MOSFET, and this is source, this is drain. This P channel MOSFET will get active only when VGS would be negative, VGS would be less than value, that is VGS would be less than, that is the value at this point, the value at gate should be lesser than source. VGS should be negative, right? So the voltage at gate should be less than the voltage at source, right? So what will happen if this signal is generated? Then the voltage over here would be same. So we have to check for the V5 reference sus, and for checking this, we have already seen this is connected to the 5V underscore S5, and you can see this 5V underscore S5 is coming from this 5 volt LDO output of 3.5 regulator IC, and it is becoming 5V-S5 via a MOSFET. And this is a P channel MOSFET. You can see the arrow is outside. In the P channel MOSFET, this gate is connected with a signal, and suppose this signal is not over there, then this P channel MOSFET is turned off, because the voltage at source is equal to voltage at gate, because this circuit is not there. Since it is not, this signal is not coming over here, this circuit is not there, this is directly connected with here. So the voltage at gate is more or less equal to the voltage at source. So this MOSFET would get turned off. To turn on this MOSFET, the voltage at gate should be less than the voltage at source, because we know for P channel MOSFET VGS should be less than a specified value. And if this signal is coming, you can see this signal is ending with hash, and hash means if this signal becomes active, then value 0 volt would be there, less ground 0 volt would be there. That means 0 volt means ground. So this ground is shifting over here, so the value voltage at gate is 0, whereas voltage at source is 5 volt. So VGS is less than a specified value. This MOSFET would get turned on, and this 5 volt, this current will flow from here, so the value will become 5 volt. So this 5 volt would come over here. Now we have to check from where this signal is coming, so we'll search it, and you can see this is generated via a simple AND IC. And what is the operation of this AND IC? VCC is connected with the 5 volt S5. This is already generated 5V underscore AUX underscore S5. This is already generated via the 5, this is LDO output, 5 volt LDO output of 3.5 regulator IC. Now what are the two inputs? This IC works on a simple phenomena of A plus B equal to Y. That is, if both A, B are okay, then Y would come. Now what is A? A is E EC reset, and EC reset is generated via this 3.3 AUX. This is already generated, and we can see from where this KBC underscore 3, we'll just copy it out, and that would be very simple. We'll just copy this and we'll paste this, and we can find it. We can just find where this is coming. Now we can see this KBC 3D3 AUX S5 is coming from this, the 3.3 LDO output via gap register. So if this is not coming, we have to check this gap register. We have to just clean it and it would come. Now we'll go back. So this is already there because we have already checked that this is 3.3 LDO output of 3 volt 5 volt regulator IC, and since we have already checked this in the previous stage, we have already checked in the RT VCC RTC, so this voltage must be there. Now this voltage is connected via this resistor and it is giving EC reset. So EC reset would also be there. If this is there, then EC reset would also be there. If it's not there, we have to check these two components. Now A is there, we have to check B. So if A and B are there, then Y would come. Now A is 3.3 volt and we have to check the S5 underscore enable. S5 underscore enable we have to check, and we'll go and see where is S5 underscore enable, from where this is coming. Now this is written page number 31. Page number 31. So S5 underscore enable is the output of the IO controller, and when would this IO controller give output? When it will get its important inputs. And what are the important inputs? We have already discussed. Supply is there, 3.3 volt is there, EC reset is there, and clock is there. We have already talked supply, reset and clock. So the supply, reset and clock is there. The embedded controller, the EC inside this IO controller, will interact with the EC BIOS via this interface, the X bus interface. We'll go at page number 33 and we'll check for these three signals. If these three signals are there, that is EC is interacting with the BIOS interface. If the signals are not there, then EC is not interacting with the BIOS IC. In that case, this BIOS would be problem, or the program inside the BIOS is problem, or the EC inside the IO controller is problem. So we can verify it via oscilloscope by checking the signal clock enable and read via oscilloscope. We'll find a signal waveforms, and if there is no signal waveforms, then we can tell that EC is not reading the EC BIOS, and in that case there would be a problem in the BIOS chip or with the EC program. So we have to reprogram it. While I am speaking all these things, I will test it on a practical notebook motherboard. First we are learning the steps, right? So always try to rewind my videos and listen it properly. So what I have told, EC, the IO controller has got supply, reset and clock. Now the EC inside the IO controller will interact with the EC BIOS present in the BIOS chip. So how can we check this interaction? We can check this interaction via an oscilloscope, right? We can check this interaction via oscilloscope. Now we have already checked this, so we'll go to the page number 31. So the EC has got the inputs. EC is reading with the EC BIOS. Now it will generate S5 underscore enable. Now there are two conditions. Suppose your notebook motherboard is connected with a battery. In that case, after you press power button, then this signal would come. And if your notebook motherboard is connected with a charger, then without pressing power button, this S5 enable would come. Now how can we check this? How would this IO controller know that it is connected with the adapter or not? So we'll just go and search for ACOK. Right, and we have reached the charger IC page. Now we search for the ACOK. AC underscore OK. You can see this AC OK is connected with the AC underscore OK. Sorry, yes. So we have reached the AC underscore OK. Now this AC underscore OK is the output of the charger IC, and when this AC OK would come, when AC in DC in is coming, then the charger IC would generate, go back, read my class, listen my class of charger IC. I have already explained how this AC OK is coming. So this AC OK would come at the gate. This is N channel MOSFET, so the current would move from the, if this AC OK is coming, then this MOSFET would get turned on and this 3.3 volt would come here. AC underscore in, that is 3 point ground would shift here. So this AC underscore EN has means it would become active at 0 volt, and when this MOSFET would get active, the ground will shift over here, the current will move here, the voltage would become 0. Now this AC underscore IN, where it is going? It is going to the IO controller. You can see this is the input. AC underscore EN has is the input of this IO controller. So this signal will determine if this ACN is low, that means the EC inside the IO controller will know that yes, it is connected with the adapter. In that case, S5 enable would be generated immediately after getting the inputs and reading EC BIOS. And if this AC underscore EN is high, that means the EC inside the IO controller will know that no, it is not connected with the adapter, it is connected with the battery. In that case, you have to press power button, and then this S5 underscore enable would come, right? Then this S5 enable underscore would come. So for checking, we can see over here, for checking V5 reference SAS, we have checked entire IO controller, we have checked the entire charger IC, right? So this is the correct step. By checking each of the signal in the power sequence, will eventually check all the important things and will not miss those signals, right? For generating V5 reference SAS, for generating this voltage, we have checked the IO controller, we have checked the EC BIOS, we have checked the 3.3 regulator, right? So we have checked all of them. Now we'll go to see the fourth one in our power sequence. We can see what is the fourth voltage. What is the fourth voltage that is required by the ICH? It is VCC SAS 3 underscore 3. And I think I have missed one more point, is that INTVRMEN, this is in point number 2, this stands for internal voltage regulator enable, right? And this signal should always be high. It is connected with the 3.3 regulator IC. You can just copy it and we can see over here from where it is connected. You can see this is INTVRMEN is connected with the RTC VCC. We have already covered. This is the first step, right? So this signal should always be connected over here. This resistor should be okay. If this resistor is not okay, internal voltage regulator will not work and your ICH won't work, right? So this is the way we have to check. Now we'll go and check VCC SAS 3 underscore 3. I have already spoken. ICH, any IC which have ACPI, advanced configuration power interface, which support ACPI, will have three kind of power rails, that is RTC rail, RTC well, suspend well and core well. So this SAS stands for suspend well. So first of all, RTC well will turn on, second suspend well will turn on, and the third is core well would turn on. So we have already checked RTC well has turned on. The suspend well we have checked 5 volt. Now we'll check the 3.3 volt. Okay, so now we check this VCC suspend 3.3 volt. And we have already checked this 1, 2, 3, and we can see the ICH 9 requires three kind of suspend volt. One is V5 references, that is reference for 5 volt tolerance on suspend valve inputs. This we have already checked how to check this. And the second is VCC sus 3_3. And what is this voltage for? This is 3.3 voltage supply for suspend valve input output buffers. Now we'll check from where this VCC sus 3_3 is coming. So what we'll do is we'll just select it out and we'll go into the schematic diagram and we'll search for VCC sus 3_3. So this VCC_3 is 3.3 voltage for suspend valve inputs, right? This is 3.3 volt for suspend valve input output buffers, right? Input output buffers. Now this VCC sus 3_3 is connected with 3D3V_S5. So we'll check from where this 3D3 this voltage is coming. We'll select this and we'll just paste it out. We'll see from where this is coming, right? Now obviously it would come from the 3.35 volt regulator IC, but we are checking how it is coming. Now you can see 3D3V_S5 is generated from 3D3V_PWR via a series of gap resistor. So we'll check this gap resistor and we'll check this. And from where this is coming? This is coming from 3D3V_power R is generated by switching these MOSFETs by this regulator. You can see these two MOSFETs are connected. Drive high 2. Now this drive high 2 is connected over here. This is going to the gate of MOSFET of upper MOSFET. Someone calls it top gate MOSFET, some call this bottom gate MOSFET, some call this TG, some call this DG. So this 3D3V_PWR is generated by this IC 3 volt 5 volt IC by switching this MOSFETs. By switching this MOSFET, DC bat out is converted into 3D3V PWR, which is eventually 3D3V_S5, which is feeded to the VCC sus 3_3, and this VCC sus 3_3 is the supply for the suspend valve input output buffers. Now we'll check. So to generate this drive high 2 and low L2, drive high 2 and L2, this signal is coming from this 3 volt 5 volt regulator IC, and to generate drive high 2, this EN2 enable 2 must be there. Now this enable 2 is connected from this signal. Now we can check from where this signal is coming. We'll just copy it out and we can paste. Now this, you can see this signal is coming from this MOSFET, right? This signal is coming from this MOSFET. This is a N channel MOSFET, and this voltage PWR S5EN has, we have already checked how it is generated. This is generated via a, this is generated via a, this is generated via a AND IC, and we have already checked in the previous stage. While checking this V5 reference sus, we have already checked how this gets generated. All right, so this is already there, and we have to check for this MOSFET. This is a N channel MOSFET, and if gate for N channel MOSFET to operate, VGS should be positive, right? VGS should be positive, and this signal would now get connected. This PWR S5EN1 would get connected when this gate volt would come over here. When this gate volt would come over here, then this PWR S5EN1 would get active, and while it get active, the EN2 will become active, and EN2 will become active. Then this drive high and drive to this 3 volt 5 volt regulator IC is having internal, will generate this drive high 2 and drive L2, this L2 51120 L2 and high 2, and will switch these MOSFETs to generate this voltage. So if this voltage is not coming, we have to check for these two MOSFETs, the top gate MOSFET, bottom gate MOSFET, this inductor, this capacitor, and we have to check this input at the gate. If these inputs are not coming, then we have to check the enable 2. If enable 2 is there, even though it's not working, then we have to check with whether this IC is okay or not. We have to just replace this IC, right? So to generate this VCC sus3_3, we had tested this 3 volt 5 volt regulator switching operation. Now the switching operation comes in place. Before that, we were just checking the LDO output, the 5V AUX S5, the 3D3V AUX S5. So this power supply, this VCC sus3_3 is supplied by 3D3V S5, and this 3D3V S5 is generated by this 3 volt 5 volt regulator IC by switching these MOSFETs. So this 3.3 volt is different than this 3.3 volt. This is LDO volt, it will get out directly, whereas this 3.3 volt would come after switching this MOSFET. So how would this MOSFET switch? It must get voltage, it must get gate signal, and when this gate signal would come, it will come when this enable 2 would come, and we have already checked that this signal would come from where? It would come from a gate IC, A plus B equal to Y, and where is B coming? B is coming from the IO regulator. So we have to test the IO regulator, and how regulator is generating B? We have already checked it. It is interacting with the EC bias, getting inputs at the IO controller, and then generating S5 enable, and then becoming this signal. So by testing, by checking the motherboard in this sequence will not leave any important things. So I am reiterating that follow my procedure of testing notebook motherboard. So we have checked 1, 2, 3, 4. And this VCC sus is supply for the suspend well IO buffer. So in the RTC well is okay. Now we are checking the suspend well, and in suspend well, what are the three voltages? One is V5 reference sus, this is 5 volt tolerance. The second is VCC sus 3_3, this is supply for the suspend well input output buffers. And the fifth one we'll check is VCC sus 1.05. and what is this for? This is 1.05 supply for suspend well logic. So three kind of volt. One is tolerance, second is suspend well input output buffers, and the third is suspend well logic. Now we'll see from where this is coming, and as it is written, this voltage is generated internally. So these pins can be left as not connected. We'll check in a schematic diagram. VCC sus. Now we can see this VCC sus 1.05, they are left as not connected because they are generated internally. And how they are generated internally? We have already told that ICH9 has many internal voltage regulator, and when this signal comes INT VR MEN, then internal voltage regulator is enabled. So this 1.05 volt would be generated internally. So all the three suspend well voltage have come. Now we'll check point number 6, that is RSM reset. Okay, so we have checked this the RTC well and suspend well. Now we'll check for RSM reset. What is RSM reset? This is resume well reset, and this is input in ICH, right? So we'll check, and this signal is used for resetting the resume power plane logic. So we'll check in the schematic diagram the RSM reset has, right? RSM RST has, and you can see the RSM RST has, this signal is getting from SB underscore RSM reset, and this is coming from page number 31. It is obviously coming from the IO controller. So what we will do, this signal is also called EC reset, EC RSM reset, because this RSM reset signal is generated by IO controller, is generated by the EC present in the IO controller. So we'll just copy it and we'll just paste, and we'll go to the page number 31, and you can see this is coming out from the IO controller. Now when this will come, it will come when the EC inside the IO controller will get power, that is this IO controller gets supply, reset and clock, and this EC can read the EC BIOS via the BIOS interface. So we had already checked all these things, and when this IO controller will receive the power button signal, you can see KBC power button. When we press power button, then this RSM reset, SB underscore RSM reset will come. We'll see from where this power button signal is coming. You can just paste it. It is coming from the power button, and you can see here it is a power button, and you can see this is power button. This is connected with the 3.3 LDO. So when you press power button, the ground will come over here. So this you can see this is hash, that means 0 volt would go there to the IO controller, because there's right now when you do not press power button, there is no path, so there is 3.3 volt. So before pressing power button, what you have to check at this point, you have to check your 3.3 volt is coming, your 3.3 volt is coming this is coming from the LDO, right, AUX. So 3.3 volt is coming, then you can ascertain that your LDO volt is okay. Now when you press power button, the ground would shift here, because you press power button, the ground would shift here, so 0 volt would be here and it will go to the IO controller. So when the IO controller, the EC inside IO controller receive this signal, then it will generate the RSM reset. Now you can see there is also a power LED, right? And this power LED, here there is a transistor. Here there is a transistor. You can see base, collector and emitter, and you can see this is PNP. How this is PNP? Because arrow is inside. P base, N, P is emitter, N base, C is collector. So you can see PNP. This is PNP transistor. Now in this course I have been discussing always MOSFET, and I have been discussing transistor to a lesser extent. So what I will do is, to understand this transistor, I will just discuss little things about PNP transistor and NPN transistor. PNP and NPN transistor. You can see over here. You can see over here. This is a NPN. In NPN transistor, current will flow from base to emitter. You can see arrow is from base to emitter. So if arrow is outside, it is NPN, and in that case current will flow from collector to emitter when base is connected to a voltage. That is, if you increase current at base, then current from collector to emitter would increase. Whereas in PNP, you can see PNP, you can see arrow is from emitter to base. Current would flow from emitter to collector when base is connected to ground, right? When base is connected to ground, or when base is having negative voltage. So this is directly opposite. You can see in PNP, in NPN, base is connected with a voltage. If you increase current over here, you would increase current from collector to emitter. And PNP is different. PNP, current will flow from emitter to collector. When you decrease volt over here, when you place 0 voltage, then current would flow from emitter to collector. And you can see over here, the arrow is from emitter to base, that is emitter to base, that it is PNP. And what happened PNP? The current would flow from emitter to collector when base is connected to the ground, right? And you can see the base is connected to the power LED has. So if this signal becomes active, 0 volt would come over here, and then this transistor would work and power LED will glow. But this power LED will glow only when 5V_S3 would come. So that is, by seeing this circuit diagram, we can say that first the KBC power button signal would go to the EC of IO controller, and after some time this power LED will glow. That is, the power LED will not glow immediately because the input is connected to 5V_S3, and we can search from where this 5V_S3 is coming. 5V_S3, and you can see this 5V_S3 generated by 3V 5V regulator IC by drive high 1 and L1, and drive high 1 DRVH1 will get active only when enable 1 is active, and enable 1 is active when SLPS4 is active. And you can see in this power sequence SLPS4 becomes active after RSM reset, right? After RSM reset. So there is a difference in timing. What I am trying to explain is there is a difference in timing. There is a difference in timing. We'll go back and we'll go to page number 31, right? And we were talking about SB_RSM reset, SB_RSM RST has, right? And we'll go back to the page number 31 again. This is very interesting, because many of the students always ask, my power LED is not glowing, that means my IO controller is not working. No, there is a little bit of timing difference, and you can see this is KBC_power button. So we're trying to search this KBC_power button. Go to the KBC_power button page. Yes, and here in this page, you can see the 3D 3V is connected to the power button. When you press power button, the ground will come over here, so there would be 0 voltage. This will go to the IO controller, and then IO controller will release RSM reset signal. And you can see this is here the power switch is connected with a transistor. What kind of transistor is this? Can you tell me what kind of transistor is this? Arrow is inside, so it is PNP, and PNP becomes active only. The current will flow from emitter to collector when base is grounded, and here the base is connected with the PWR_LED has. Now this PWR LED has is coming from, we can see it is coming from another transistor, and this transistor base is connected with